Okay, go for it. Great. I am Brian. Today I will talk to you about the complexity of thermal states, specifically in fact where I'm imagining that I have a mixed state. So we've heard a lot about how to define complexity for pure states. I want to talk about how to define complexity for mixed states and how we can get some estimates, upper bounds on that complexity using some information theoretic arguments. And then in the last part, if there's time, I will try to talk a little bit about how this may relate to properties of the geometry in ADS-CFT. This is work that I've done with John McGreevy and also some work in progress with Cesar and Matt. And I also mentioned that I'll touch on a topic that has received a lot of attention recently called holographic subsystem complexity. That's sort of a buzzword in the field, and a lot of people in this audience have worked on that. So I'm going to give you some definitions and some constructions, and then at the end try to relate to ADS-CFT. So before I say anything more, let me talk a little bit about why I care. We know from the point of view of ADS-CFT that thermal states of the CFT are dual to black holes in ADS. And for my purposes, the basic picture of the black hole, I'm just going to be really simple. So I'll consider just the eternal two-sided black hole. Sorry for those of you who wanted something more exciting. There's a left and a right, and so this is two conformal field theories, and there's entanglement between the left and the right. And the entanglement between the left and the right is the thermal entropy of either side. So this is the outside, and this is the inside. And we know that this is supposed to be the same as the thermofield double state, which has some expression that I won't even bother to write down because we don't need it. And for my purposes, the physical picture of this state will be a tensor network picture where I have, corresponding to the left, some kind of renormalization group network, which you should think of as like part of a Mera network, say, where I've truncated all of the nodes that lie at lower scales, at longer wavelengths than the thermal scale. Right? So I have a big tree here. Some cross connections, which I'm not going to worry about. And what I'm doing is somewhere in this tree, there's a thermal scale here, and I simply erase all these tensors here. Okay, so I have some legs coming out that I want to do something with. I do the same thing on the other side, the right RG network. And I have some dangling legs, and I simply connect them to it. So these are essentially the EPR pairs, and how many such EPR pairs are there that will be an entropy split? Yes?
On your right picture, that's a slice of space.
Let me be ambivalent about, or ambiguous, or not answer the question. Maybe I actually want to think of this as a region of spacetime.
I mean, just because it's very suggestive, you compare that picture with the left pictures.
Yeah, I agree.
Okay.
Yeah, I have some alternate, so certainly originally we thought of these things as living in space, but maybe I like to think of them as living in ADS-sized chunks of space-time.
Yeah, whatever it is, it's time dependent.
That's correct, yeah. So here I'm sort of, sorry, this is like, there's a suppressed space, so this is space. And this is time, sorry for that confusion.
Okay, that's not.
But everything's rotationally invariant, so maybe it should be confusing.
Right.
Yeah.
Is it going to be important that you're just connecting them directly to the EPR pairs?
Let me just call this a cartoon.
Okay.
Did you have sophisticated criticism otherwise?
There are non-trivial correlators there, yeah.
Okay, so this is the cartoon, and there are various proposals for how to measure the complexity of this network, which for me just basically means the number of tensors, let's say, holographically, the volume, the action, and various other ideas. And so one question we'd like to know is, we have these various calculations we can do holographically that are eminently feasible, but when it gets down to it, we don't really know that much about the complexity of the conformal field theory. Okay, so we'd like to have more insight into that structure, and to know if this cartoon is even remotely accurate. And also ultimately, I think I would like to know, is it volume or is it action? Perhaps these merely correspond to different definitions of complexity, but maybe there's a more significant difference between these things. This is one. And so one of the things you might do is try to probe pieces of this network as a way to understand in a more refined fashion what the correspondence is between holographic geometry by some measure and the pieces of this tensor network. So that's kind of what I'm trying. That's the motivation for me at SITP, is I'm trying to get at pieces of this. The other motivation is the reason why I'm interested in this topic is because I'm interested in simulating non-trivial systems on interesting engineerable hardware like cold atomic gases. And the reason why I'm interested in doing this is because, well, first of all, there's a very basic reason, which is that we don't know whether quantum mechanics is really correct all the way down to the bottom. Could be an effective theory. And in my opinion, one of the places where it's the least tested is in complex many-body systems that are isolated from their environment. It's going to be hard to see a deviation from quantum mechanics and Qubit rates because there are so many other things going on. The other reason to be interested in this, I think, is that you can do nice, clean, controlled experiments, including experiments that would not be possible sort of in vivo. For example, you can, in some of these setups, you have sufficient control over the Hamiltonian, over the dynamics, that you could reverse the flow of time and effectively rewind and fast forward the system coherently. Right? So you can do experiments, for example, to probe chaos we've heard about a little bit. In these systems, you just couldn't do if you just had the quantum field theory in nature that you accessed via your collector. Okay. And so, from this point of view, where we don't quite have these quantum simulators yet, but we will soon, it becomes, in my mind, very urgent to understand exactly how complicated what we want to do is, to understand recipes for building these interesting kinds of states from simple ingredients. So I think this complexity question really is important. And then if ADS-CIP can give us some insights into how complicated things are, how we might form them, and so forth, that's an interesting connection. Okay, and then I'll also just say that I think the process, this was mentioned by John yesterday, the process of going through thinking about how to do the simulation is a valuable process. And for example, you may think about the effect of noise in your simulation, which is not a question you might have ordinarily thought about, and that may lead you to some of these ideas. So these are the two reasons why I'm interested in trying to understand the complexity of these states. We'd like, for example, to set up a thermal state and then study real-time dynamics of that state. That would be a very interesting experiment to do. So let me tell you the setup now. I'm going to have a Hamiltonian, big H, some temperature, T, and my state will be the thermal state of that temperature. And just to be concrete, I'll assume that it's just in qubits. So clearly some of what I'll say can generalize, but I'll just work in this simple setting. And so we have this mixed state, and we'd like to know how to think about the complexity of this mixed state. And I'm going to give you 3 definitions of this complexity and discuss their relative features and merits, what we know about them. And I'm going to imagine, to start the thing off, that I've fixed some C0, which is a pure state complexity. So I make all the choices you have to make. I fix a universal state. I fix a universal set of gates. And this is the data into my construction. So first definition.
Right, so C0 is what we sometimes call a reference state?
No, C0 is a rule for calculating the complexity of a pure state.
Oh, okay, I see.
So, so in other words, C0 is for any number of qubits, start it all up and use any 2 qubit gates. No, like Scott, I will allow ancilla. In fact, that'll be important in this, as you'll see in a second. So definition 1, I'll just call C because I think it's the best in some ways. So I won't give it any subscripts or superscripts. The complexity of a mixed state I define to be the minimum over all purifications psi. So I trace out psi I get rho of the pure state complexity of psi. That's gotta be the simplest thing you can imagine. You just take a pure state, look at a set of all purifications, and you ask, among all those purifications, I calculate the pure state complexity, and I simply find the minimum value. Now, my intuition for this quantity is that it somehow measures it measures the complexity of the spectrum and the complexity of the eigenbasis of rho. So it's hard, you know, it deems you when you make both of these things. So if you rotate from to a non-trivial basis, it calls complexity, and if you make spectrum, it calls complexity. Yeah.
If you take the size of the purifier to infinity, it's still bounded on the continuum.
Well, so, I mean, I can always purify on a system of the same size.
You can, but if you take a larger purifier, then you
Right, but I'm minimizing, so.
it doesn't help. It doesn't give you a lower value.
No, I'm not claiming I know what this is. I'm just saying this is a definition. I don't know what
I
this
guess you're
is.
saying, or you know that it stays above 0 even if the auxiliary space becomes infinity.
Yeah,
Assuming rho is of the thermal form,
yeah, let's say. That's what I have in mind.
so I guess the answer is the thermal field level.
Yeah. So I'll show you in a second. We can use this to give an upper bound on this by giving explicit construction.
So, Brian, so for maximally mixed state, the complexity is like
Sorry?
for maximally mixed state, by purifying this much of it.
Yeah, it's N or 2N, depending on what my gates are. Yeah, great question. I'll come back to this in just a second, give you 2 examples.
Wait, I mean, these are completely general definitions. I mean, why do we have to focus on a particular state?
No, we don't.
Yeah.
I'm simply, for the purpose of concreteness,
Yeah, fine,
I'm
fine.
focusing on this
All right, fine.
particular state. But yes, absolutely, these are general definitions.
Yeah.
I don't have to say anything about the particular state here. Okay, second definition starts from this definition and says, well, okay, I had this intuition that it's counting the spectrum and the eigenbasis. So maybe I could have a mixed state which is diagonal, but has a very complicated spectrum. So in other words, there's a probability distribution of classical variables that's very complex. And maybe I don't want to count that for some reason. So another definition would be that you could define the subtractive complexity, which is this definition here minus the minimum over all psi such that trace over psi equals sigma, and sigma has the same spectrum. Oh, sorry, I wrote down here. I apologize. Minimum over all psi, they give you sigma such that the spectrum of sigma is the spectrum of rho.
Sorry, the minimum of what quantity?
Hold on, let me finish. So in other words, here I require that the purification reproduce the entire state. Here I only require that it reproduce the spectrum. So certainly this is an example of that, but this is going to be in general small. Okay. And if it were diagonal, then these would be equal and it would be 0.
Why would you do that?
Sorry.
I mean, you want rho, right?
Yeah.
So if you
But-
prepare rho in the basis where it's diagonal, that's not the same as preparing.
Here's my intuition. This thing here, C, of the thermal state, is maybe, or this is a question mark, is like the network including the bell pairs, and this is like the network without the bell pairs.
Well, you know, he's trying to pick apart the distributional part and the basis rotation part of the complexity. Just like Charlie was trying to pick apart two different attributes.
That's right, yeah, I was subtracting that off this point. So I'm trying to tease apart everything as much as I can to get out the different aspects of the physics.
So you could imagine that this is the complexity starting from a state which has the same spectrum,
Sorry?
right? You could imagine that this is basically the complexity starting from a state which has the same spectrum.
Yeah, that's
But it's not clear that this is the right.
That's
the
right.
complexity will be the sum. It's an upper bound.
Yeah, it's an upper bound, correct. Correct. Okay. So this is a subtractive thing, and then I'll make one more definition. We could view rho as a sum over some pure states. This is an ensemble of which gives you rho. And I could then define the ensemble complexity of rho to be the minimum over all ensembles of the average complexity of the ensemble. This is another definition you can look up. And so we have these definitions that Matt and Cesar and I have been thinking about for a little while. And so recently I made the trek to Austin to ask the Oracle what was no. And he told me the very profound fact that that this was less than that. So this is a positive quantity. But he also told me a more profound statement, which is that this ensemble complexity could in principle be quite large. So we don't have a lot of intuition for how this behaves. There's a feeling that it can't be much smaller than these two things, say C, because with some small tolerance, say, you can always throw away very complicated states. So probably if you have a very complicated state here, you can throw it away and you get something more average complexity. But possibly this is a more complicated, possibly this is a much larger measure of complexity. For example, if I took the thermal ensemble and the energy eigenbasis, and I assume that all those energy eigenstates are exponentially complex, which is not a terrible assumption, then this would be exponentially large. However, I'll show you in a moment that C can actually be polynomial sized for a thermal fluid. Yeah, Veronica.
So in the first definition, you have enlarged the space by either doubling it or taking some larger
Yes.
purifier. And then the reference state was what? I mean, here.
It's still always 0, so I just tensor a bunch of extra zeros on, and then make a transformation.
Wait, so you're saying for the thermal state, every possible decomposition you're conjecturing, requires states with average exponential?
No, I'm saying I don't know that, but that's what we were talking about this morning.
Oh, all right. No, I mean, the example that convinced me was just take, a random quantum circuit and
Yes.
just throw away half the qubits and look at the density
Yeah.
matrix of the remaining.
Yeah, so the circuit that prepares the thermophile double will not be of this random type. I mean, it has a lot of structure, but that's why I was discussing
okay,
this sort of,
all right.
maybe there's still enough
Okay, fine.
that at least within this class you can convince yourself that this is very large. Yeah, David.
Which of these definitions are reduced to the pure state definition when you apply it to
Yeah,
pure state?
great question. So suppose rho is a pure state, then C naught equals C equals CS equals CE. Suppose rho is maximally mixed state, then C naught does not make sense. C is, say, 2n, like I could apply Hadamard and then C naught for every qubit. CS is actually, again, to CS equals 0. And CE may be like n over 2. Like I need to flip every bit and that occurs with probability 1/2. So the average here. Okay. So they kind of all agree. These two roughly agree for the maximally mixed state. This effective is 0, and for the pure states they agree.
Brian?
Yeah.
So the definition of complexity for mixed state by Hastings definition
Definition 2.
is the one given by Hastings.
I think Hastings says that I'm allowed to prepare a complicated classical model distribution and then apply a short dead circuit to it. That's the definition of a topologically trivial thermal state. So yeah, I guess that's like 2. Okay, so now I'm going to tell you very briefly how to give a bound on this complexity C. Bound on C for thermal states. And so what I want to do is I'm going to explicitly, well not explicitly, but I'm going to tell you, I'm going to give you an argument that shows that there exists a circuit of certain complexity to prepare a purification of the thermal state. So the idea is let's consider a system, one-dimensional system for simplicity. Well, the argument works in higher dimension as well. You would choose the geometry right. So I have a small lattice scale little a. At finite temperature, let's suppose it's some conformal field theory. So there's a finite thermal scale, thermal correlation length C. And then I can consider some larger scale that I'll adjust, called curly L, which will be like some kind of blocking size. And the idea is what I want to do is I want to consider, say, in this line, my system, for simplicity, let me consider 3 regions, A, B, C, like this. And these are all, say, of length L. So it's not to scale. And the idea of this construction is to say, okay, correlations are short range in this state. Somehow, like, what's over here doesn't know what's happening over there. So intuitively, it should be possible to assemble this state from its pieces by gluing them together locally. Like, in other words, like, the idea is I could take chunks of this state, here and here, overlapping chunks, and kind of piece them together and produce the entire of its images. Now, a way to make that rigorous is to use the recently developed and rapidly ongoingly developing theory of quantum Markov chains, or proximate quantum Markov chains. And the way that works is you calculate a quantity called the conditional mutual information, which is the thing that appears in Strong's additivity. This quantity here. So that's the entropy of this bit. That's the entropy of this bit minus the common minus the total. And if these were classic probability distributions, so classically, IAC given B equals 0 implies that A, B, C form a Markov chain, which means that the state of C is independent of the state of A given B. So correlations are mediated through B, which I think expresses our intuitive idea that here somehow you glue locally and that's giving you the full state. So quantumly, it's also true that, and the recent development has been about saying it's not exactly 0, but approximately 0. Then it means that rho ABC can, in a sense, be reconstructed from rho AB and rho BC. So from the pieces, one can construct the entire state. And there's a formula, which I'm not going to write down, but the formula exists. It's a very beautiful formula. And you can look in the papers for that formula. You can search John and I's paper, and there's a reference to the relevant literature. This was really started by development of Fawzi and Renner, and has since developed very rapidly. Okay. So what's the physical output of this picture? Is that effectively what it says is, I process through everything that goes on here, that if I take this thermal state and I block it into regions of size L, and there's a lot of little qubits here, then by applying, say, a circuit like this, some finite depth circuit acting on roughly L degrees of freedom at a time, then I can get a good approximation. Now let me be a little careful here. This L, and I take 2 copies of it, right? I have 2 copies of the system. Then this is equal to this U low depth acting on 0 tensor 2n. So in other words, I can prepare a purification of thermal state. Let me write it this way. What this implies is that the thermal field double state is approximately some low depth circuit acting on 0 tensor 2n, where here what this means is it's constant depth, but the circuits act on degrees of freedom over size L. And remember, L is something that's bigger. I had to choose L to be bigger than the thermal length to get this condition mutual information to be approximately 0. So I think, if you say I'll take all the words away, it's intuitively very reasonable. It just says I can construct a wave function by acting on thermal scale patches, and that's it.
How does depth depends on beta?
So the depth, the dependence on beta comes in L. So L, for example, for a CFT, I need to have L bigger than the thermal length, which goes like 1 over the temperature. So as I lower the temperature, the size in which my circuit acts must be larger. But this argument doesn't tell me anything about how complicated the individual circuit elements are. In any event, it gives you an upper bound on the complexity. I made an explicit circuit that constructs it. I proved it existed, which works like this. I chunk the space into, so this is the total size, capital L is the total size. I chunk the space into chunks of total size little l, and then within that chunk I have no idea what the circuit is. So it could be as bad as you want. So there's some exponential of the Hilbert space dimension, that's an exponential of the number of qubits inside little l. So that's little l over A. So it scales with the volume of the system, but because I know nothing about, from this argument, what happens beyond this little scale L, I have to put the worst possible bound edge. And if say, I can get away with L equal to constant, then this is still polynomial complexity. It's, it's like linear into some size complexity compared to the state. Okay, any questions? Yeah, all right.
So you took the purifier to be larger than the subregion. Do you have any idea how process would have gone down?
I took the purifier to be larger than, sorry, say again, I didn't think I understood.
Instead of doubling the degrees of freedom,
Yeah.
you can get away with it. You might have naively expected that by taking a larger purifier, you get a smaller number for the complexity.
But I guess if I'm really using these more degrees of freedom, I'm just acting with more gates, right? Like, that's my, I can't prove to you, but my intuition is that if I had a bigger purifier and I was doing something non-trivial there, it's just costing me more.
So you would
gates.
guess that the entropy, that the complexity is larger, that this is the big one?
No, yeah, I think you can't do better by introducing an extra, like additional stuff. But that's just a guess, so I
But
emphasize.
this formula is for one layer, right?
Yeah, so, okay, but
Yeah, okay.
some number there.
And
And I can make this, by making this L, say, logarithmic in system size, you can achieve an overlap with the thermocool bubble, which goes down like 1 over a power of system size, so very close. And that would still be polynomial complex.
Could you compare the complexity of different temperatures in order to get rid of this A cutoff?
Yeah, you can. Here, if you subtract them, you wouldn't get rid of the A. So, but I emphasize that this is an upper bound, and I think the complexity is smaller. We just can't prove that yet.
Yeah. Grows as you go to lower temperature?
Sorry?
How does the complexity behave with temperature?
Yeah, so this L must be bigger than 1 over T. So this upper bound will diverge rapidly.
So the vacuum is a very complex state.
Well, it's in fact not that complex.
Right.
So I can give a different argument for the vacuum. At some point, this will become an inefficient construction.
Yeah, so say say the temperature is order the size of the sphere.
Yeah.
Right, and then some of this.
Yeah, this is just a bound, and it's just a very bad bound if I'm at very low temperature.
But you can't extrapolate all the way to 0 temperature, because, I mean, holographically, put all this in the gravity language, you would have been stuck with large black holes, and that doesn't, and you can't go to a small black hole and make all this to work.
Yeah, so there'll be some phase transition, let's say, and the complexity may change
Right.
discontinuously. But I emphasize the ground state you should regard as easy. Like that's what I told you 7 years ago. The ground state is Mera. That's what Ephraim told us. The ground state is Mera. Its complexity is relatively small. So for comparison, the complexity of the ground state we expect to be of order all over A. So, Jordan.
So this is assuming that your Hamiltonian question is like geometrically local or something?
Correct, yeah.
So are there any particular assumptions that you need to make about, I mean, what other assumptions are built into Hamiltonian this look like?
Well, the assumption is really that these conditional mutual informations are small. So let me say a word about this and advertise my elaborator's work. This, we can check for free particles very easily, not just in thermal equilibrium, but also out of equilibrium. So like if you drive a current through the system, for example, you can still check that this is true. We can also check using ADS-CFT. We can compute these mutual information, these conditional mutual informations fairly straightforwardly, at least for certain geometries, and we can again check that they are, say, exponentially small once L is bigger than the thermal. So with a weak and strong coupling in a variety of states, we can check that this sort of assumption is true. And there's a general sort of argument based on the path integral that this should be good as long as you're connected to infinite temperature without encountering a phase transition. That somehow this should vanish. Yeah, separate.
So if you try to expand your Hamiltonian and evolve it in imaginary time, you also get the state, right?
Yes.
Does it give you a similar bound, or?
I guess that there I don't know how to turn those non-unitary gates into unitary gates. That could be bad, right? Like for example, to make the toric code, I can project using these non-unitary gates and prepare the toric code ground state in one step. Or if I want to use a unitary circuit, I know it has to have depth, which grows with system size. So I think there's some subtlety. Maybe it's not that bad. Maybe it's just a small blow up, but I think there's a subtlety in using that. Yeah.
So it's connected to the non-unitary gates. I guess there's a fourth definition I was expecting.
Okay.
Which was
Do tell me. Yeah.
Yeah. The length of the shortest mixed state quantum circuit that would prepare. Mixed quantum circuit that would prepare the states.
Mixed quantum. You mean like a
Completely positive map.
Okay. Yeah, I see.
So that would give certainly an upper, lower bound on the other one, the first definition.
Yeah. Okay, that's interesting. I haven't thought about that.
That's somewhat connected to that question. So,
Wouldn't that be the same as if I
It's- because it gives you, the optimal circuit would give you a purification, but it's not clear that it's the optimal. Maybe it's trivially the same.
Yeah, I don't know, that's a good question. I haven't thought carefully about that. Yeah, Charlie?
Your remarks about the conditional mutual information, do you have any, or maybe anybody else here, have any insight on whether the give space rule applies to equilibrium states of quantum systems?
I mean, that somehow my understanding is that Gibbs space rule is parameter counting in some sense. So,
Well, I mean, yeah, that's the way you use it, but the point is that if you have parameters which ought to break some symmetry, and you've broken all the symmetries, you should have only one stable Gibbs space.
yeah, so let me say, certainly for the things that I talked about where this is actually true, there is only one stable state. And moreover, there's no phase transition to go from that state to infinite temperature. So it's smoothly connected to infinite temperature. And I think that then we're very safe. Now, we could talk about topological, these kind of like toric code in higher dimensions, this kind of thing. And actually there's a generalization of what I told you, where you take the thermal field bubble at some size L, and you can relate it by some kind of low depth circuit to the thermal field bubble on a smaller size times a bunch of extra stuff. So there's a generalization of this low depth construction, topological states at random temperature, which will remain topological. So for example, the toric code in 4 dimensions. But for simplicity, I wouldn't do that. And then this conditional mutual information will fail, because you have to essentially look at you have to look at regions. So in higher dimensions, the way the construction works is you sort of do a cellular construction. So you start with your 0 cells, and you glue 1 cells together to make a skeleton, and then you glue the faces and so forth. And if you do this, you'll find that there are obstructions which say that this information is not vanishing if there's a topological state present. So that's how you detect if there's something lower. Okay, I think I must be running out of time, well, I'm not sure. So let me just say a little bit about holography, and then how much long? 0?
More than 10 minutes.
Oh, it does. That's plenty of time.
Is that a crude upper bound, or is it
So I crude upper bound to what?
how much?
When you finish.
Sorry. Can you repeat the last part?
I say, is the 10 minutes a crude upper bound or a tight upper bound?
Oh, I don't know. Is it?
Becoming increasingly tight.
So let me bring it back now to ADS-CFT. So recall I had this bound that said this was L over little l times the exponential of L over A. This is a bound, but we think it's on the tight bound. That is, we think the complexity is lower than this. In particular, the complexity, that little picture I drew here. This complexity would be smaller than this. And essentially, as I said, what we've done is we've not looked inside the hood of these thermal scale.
That's the number of
Correct, number of tensors. Okay. So we haven't looked inside the hood of these thermal scale objects these big blocks that we use to construct. Okay. So if we look inside those blocks, we will find, for example, that for scales much smaller than the thermal scale, it should look like the ground state. And so I should have the ground state network being a good approximation, again, of physics. And so the idea is that the true complexity there's a much tighter bound. Let me write it this way. This is a loose bound, we believe, and can prove in some cases that it's loose. And so a tighter bound would be that the complexity is something more like L over A, plus something of order the entropy. So actually, maybe 2. In other words, the physical picture here is that if I say compare this to the ground state, 2 copies of the ground state, then I've lost a bunch of tensors here. And how many tensors have I lost roughly in entropy's worth? But I've gained tensors here because I have to create the bell pairs. So it's not obvious that you get any savings. Right? And this has actually been a point of debate in the recent literature about whether the complexity of the thermofield double should depend on temperature at all, and how it should compare with the complexity of 2 copies of the ground state. And in fact, volume and action give different answers for this comparison. However, we could circumvent this issue again if we could probe sub-pieces of the network. So what I'd like to do is, in the last few minutes, tell you about an attempt to probe, like say, the sub-piece of this network using this subregion complexity.
So could you say what you get for, if you do the volume and action conjecture, what is the difference?
Let's see.
I don't remember that.
In ADS3, let's see, is action, it's plus C, and volume is minus C.
It was only different by a small amount.
In ADS3, they differ by a constant. I guess action is probably smaller and volume is bigger. Is that right, Rob?
They differ by a constant of order than the entropy, is that correct?
No,
Yeah.
constant independent.
A constant of order of the central charge, but not dependent on the entropy.
Okay.
In general, you might expect an entropy dependence,
Right.
which I guess does occur in higher dimensions. Right.
It also depends on the choice of vacuum.
That's right. That's right.
What do you mean, Joseph?
You can compare the Noah Schwartz to the Ramon.
Okay, but that's an important fact, but too fine-grained for our story today. Okay, so let me take again my black hole. And I'm going to consider a special simple subregion, which is just the entire left half. Okay, and the rule is one is I take the subregion X. I find the RT surface for X. 3, I find the entanglement wedge. E of X, which just means, in this case, this entire region here. And then 4, I intersect with the Wheeler-DeWitt patch. So that's this. And so ultimately I have this region here. This is the region of interest. And then 5, I calculate the action of the intersection. There's an analogous rule for volumes, but I'll take this rule. This is the obviously correct rule is to use that. The only important ingredient here is that we choose entanglement wedge, which is sort of obviously correct. For reasons I can elaborate on, but won't have time.
Wait, what is this one?
Great question. What do you think? C, CS, C, C naught,
C.
C circuit.
C.
Geometrically is very bizarre.
So you don't have subscript.
C, yeah. So in fact, we think it's C. However, it's not obvious. At first, I thought actually that it would be subtracted part, because I thought this part would be like the area, it would be like the RG part without the bell pairs. But actually, it seems like you get the bell pairs in this definition. So it's kind of
But you don't get it divergent.
no, it is. It's also divergent here.
Is it divergent?
It is divergent.
Cut it off.
Yeah, it depends on how you cut it off, of course.
Right, but there was at least one way of defining it where you had no divergence at all. Or am I wrong?
One way to define it with no divergence at all. I think it's a choice, but we'll subtract that off. So, okay, we calculated this. I mean, it's really easy to calculate using, we can consider more complicated black holes, but based on development in the field, it's now very easy to calculate the action of this region. And what we find is that the action at T minus the action at T equals 0, this is all ADS3. Just for simplicity of presentation, you can do it in higher dimensions and other kinds of black holes. We find that this is proportional, there's a number times the entropy times 1 plus log of the horizon size divided by some number, some cutoff delta we don't specify. Okay. So this is the action, to be clear, this is the action of region 1, or this is 1. And you can also calculate the action of region 4. So this is the subtraction money that gets rid of the UV divergence at the boundary.
This log is basically the same as the log that
Reason
Rob
for
was talking about.
Well, yeah, so actually, let me comment on that. So this log is a bit mysterious. We were hoping to get something proportional to the entropy, but it's only this extra log. I don't really, it comes from the corners, these terrible corners. We don't really know what it means, but maybe it's related to what Rob talked about before lunch, perhaps?
Yeah.
So
What is E set?
Sorry, good question. This is the horizon radius. I'm considering a planar ADS3 black hole, so the simplest possible black hole. And interestingly, the action in the inside, in region 4, is just minus the same number, s times 1 plus log ch over delta.
Minus C naught.
No, it's not divergent. It's just a constant.
So Brian,
Yeah.
does this suggest that there's some weird additive property of complexity where if you say if you take the whole thing, you just take the sum of these 4 diamonds? That's a geometric property of the fault.
Yeah.
Is that in general a property you expected about purification?
It's a property or observable, but
Oh, okay.
no,
It seems kind of weird.
yeah, I'm not sure. I want to interpret this. Let me say an interpretation and then finish. So yeah, I want to think of this as this is going to correspond to C. So the idea is this is my complexity C, is why I give it no subscripts. CE probably is large, let's say, or we don't know what it is. Maybe it's the same. We're not sure. This is the ensemble complexity. The subtracted complexity should go to 0 at infinite temperature. But this is growing, so that also feels wrong. So among the 3 candidates I gave you, it feels like this is the best choice. And it has a sensible interpretation. It's saying, essentially, that the complexity of preparing the thermal state is the complexity of the RG part plus the spectrum part. And this is slightly over-counting because the complexities cancel exactly when you look at the entire thermal field double. So the spectrum sort of counts double. Let me make that clear. So the complexity C naught, the thermal field double, is independent of temperature. And so there's a funny puzzle, which is that the complexity of the thermal state plus the complexity of the thermal state, not a puzzle, but an interesting observation, this is less than the complexity, this is bigger than the complexity of the thermal field double. And what have we done? Here we're using 2 different systems to purify. But here we get to use the same system. One is the purification of the other. So I want to interpret the region behind the horizon as saying, well, actually, when you look at the whole thing, there's a shorter circuit because you're essentially able to use the purification of one as the other. And so that's why this is positive. It's saying that when I compute the entropy of this relative to the ground state, say, at the complexity, I lose some down here. I gain more back from the spectrum, but I gain more than I've lost. So it actually goes up with temperature. However, when I add back in the behind the horizon regions, that's telling me that there's actually a shortcut because I can use the left as the purification of the right. Okay, that's the punchline. There are lots of generalizations of this that we're working on, and I'd love to know if this interpretation that I gave has its muster. If you have further checks or ideas, I'd be happy to hear them. So let me summarize quickly. What I did was introduce some precise definitions of complexity of mixed states. And I gave you a rigorous, these definitions apply outside of ADS-CFT. I gave you a construction in the context of lattice models that can give you an upper bound on the complexity of a certain large class of thermal states. And I made some discussion in the context of ADS-CFT about how this ADS-CFT suggests a tighter bound or a better estimate of the complexity, and how thinking through these issues can give us additional insight into the different pieces of the tensor network. So we're really sort of taking space apart and understanding how all the pieces fit together and what the interpretation of various regions in space-time might be in terms of the circuit that prepares this. Okay, so thanks a lot for your attention. Yeah, Steve.
In this last part where you talked about the action of a subregion,
yeah.
Does this avoid the black hole singularity? I mean,
yeah, here it's totally outside.
So
it's just this little region here.
So this is a question you can ask. You can use the action thing and ask about not worrying about any singularity.
That's right.
Bad stuff.
Yeah.
But in your butterfly sort of elongated diagram, you could have singularity content in the common region.
Yeah, so an example where there's a problem, like if you take orbital double and you perturb one side of the shock wave,
yes.
Then if you ask the complexity of the other side, so the side you did not perturb, that side stays invariant for all time.
Yes.
But the side you perturb, that will grow. And then there'll be some behind the horizon region that contributes. So then that can be sensitive to, it's the same calculation that we did with Adam and Winnie and Dan. I didn't forget you, Dan. Yeah, Brian.
But I just wanted to make a remark.
Okay, please.
That if all these ingredients sort of are supposedly robust, then in the ADS-CFT context, this region, the subregion thing is very unnatural. In a technical sense, I can explain later, but basically it's generated by now generators, but sort of going in opposite ways on the two different sides.
Sorry, let me understand. You say the entanglement wedge or the intersection?
The intersection.
The intersection is unnatural.
It's very unnatural.
Very unnatural. Okay.
It would be very strange.
I don't know. We have to have Veronica tell us later. Yeah, well.
If I understood correctly, you were saying that the entropy of that intersection of the two wedges, it should be identified with C.
The entropy.
The entropy, the action.
The action.
Sorry. The action.
Yeah, this is terrible. I should put some curly.
That's fine. The action of that region is supposed to be equal to the complexity C that you defined before.
Yeah, that's the idea. That's the proposal.
What would you summarize the evidence for this?
Well, so this is a sort of like the picture we have right now, is that there is an estimate of the complexity of this thing coming from the tensor network where I just assume scaling, which tells me that this C will be bigger, will grow as a function of temperature. That's what I find here. It's the opposite with the volume. And there are various other checks. So for example, if you, like I said, if you take these shock waves and perturb, then you find that they grow, the other side don't grow, and so forth. So there's a relatively limited set of evidence so far, but we're working on it.
I see. So part of the evidence is that it should come from the region outside the horizon because you can always modify the other part of the black hole.
That's right.
And that should not change the complexity, so it's clear.
That's right. That's right. It has to be the
region.
entanglement wedge. That has to be.
Does the tensor network picture give you wrong?
I would say, let me be diplomatic and say, we do not understand it well enough to say whether there is a log or not.
But Rob, this is the same log?
I think it is. Well, I haven't talked to them after. I think it's the same one.
Yeah. This is the same? Well, okay, good.
I mean, yeah, I'll mention it in the sort of, in the rigorous construction I showed you before. If I really want to get very close to the state, there are also logs that appear, because I sort of need to make sure I'm getting the tails right, so to speak. So that may be related also to this. Or if I want to encode an oscillator in qubits, there's a log there. So there's lots of logs that could come.
All right, we should probably take the rest of the discussion offline. Before we go for the break, the photograph from yesterday is posted in a few places and on the table, so please just write in your name so we know who you are. And enjoy the break. Let's thank Brian.